with next speaker, Mr. Šteinbergs, from our own International Radio Astronomy Center, and with his presentation on preliminary results of Irbene interferometer monitoring in Mili-Jansky observations. Please, Jānis, the floor is yours.
Okay, so I'm going to talk about preliminary results of Irbene interferometer monitoring Mili-Jansky observations that we have done in past 2 years with a large international team. So let me talk about our aims and goals. So what we want to do, we want to use RT32 and RT16 for repurposing of a single baseline interferometer capable of leading global research in field of high mass star formation. So our goals. So what we want to do in technical side is to make a high cadence monitoring observations necessary to detect activity day-to-day year timescale of acceleration events of their long-term evolution. And then scientifically we want to detect durations and intensity of a drop in continuum emission that will reveal the physical processes involved in reduction of radio emissions from accelerating high mass protostars. So how we want to achieve these goals? So what kind of instruments? We use 2 radio sources. So this is already covered by Vladislav, so I will not going to show this again. So in our observations, we use C-band receivers, and this is where you can see images of our C-band receivers. Also already covered by Vladislav, so I will move to the next slide. So we have one baseline about 800 meters. That gives us 15 arc-second angular resolution, and because of our data processing capabilities, we can have 0.088 kilometers per second velocity resolution, and at the same time 0.002 megahertz spectral resolution. So, and what we have done is our observations can approach theoretical sensitivity limits of interferometer, that is 6 millijanskys for a 2-minute integration time. So of our observations, so we are doing typical event setup observations, calibrator, target, calibrator, and currently we have 30 target sources. So we observe each target twice in observation. So strong sources 5-minute scans and weak sources 8-minute scans. And we have 3-minute scans for calibration. And we use 16 BBCs, 8 megahertz channels, and use both polarization. So our source list comes from 2 parts. First is VIRAC single dish monitoring program that also Vladislav was briefly speaking, and also we see some results in Artist's presentation. So if we see there is some interesting sources that are very variable, so we would include in our target sources. A main list of our target sources come from high mass protostars from James Clark Maxwell Telescope Survey. And what you can see in these images, in top 1 images, you see in galactic coordinates all the target sources that we currently have. In bottom image is, so since in every observation, so what we do is we have group of target sources and we use same calibrators for our target sources. So typically we have many hours observations, and this what you see here is 5-hour observation. You see UV plot for calibrator. This is to illustrative purposes. Let me go forward. So I already mentioned data processing. So what kind of capabilities we have with data processing? So we do it in 2 parts. So we first is correlation, and correlation we do it in standard laser line correlation process that is done in Irbene and BAASP general. So we use two parts. We use continuum correlation and line correlation. In both cases, we use 2-second integration time. In continuum path, we use 128 FFT points, and in line correlation, we use 4096 FFT points. That is sufficient here, so we can detect all major features. So that is why we use 4096 FFT points. And also, we have created for calibration Parson pipeline. So that is automated way to use apes. So it's same as any other VLBI data processing. So we use untap files to gain correlations. We use bandpass flagging and frequency definition of 67 gigahertz metal lasers. We use manual phase call to remove delay and line polarizations and BBC in the phase. Also, calibration files are applied to the targets. Phase rates are determined on the maser emissions and applied to the continuum emissions in high mass protostars. Data are integrated in time and frequency and modeling to determination source flux. Diagnostic plots are produced that allow quick inspection to calibration plots. And now I move on to the calibration and some calibration results. So first of all, what you see here is 8 results. So in top part of that slide is phase and amplitude calibration with frequency for the calibrator quasar 3C3445. So, and calibration shows successful of delay, phase and slope consistency of all ifs. So what you see, phases are flattening and all spectra are consensusly. In bottom part, I'm showing the phase and amplitude versus time for all sources. So what you see in the calibration is that sources are coherent is much improvement, allowing full-time integration across the scan. So additional thing what I need to mention is left part of the slide is before calibration and right part of the slide is after the calibration. So moving forward, so another thing is what we can do is phase and amplitude calibration with frequency of high mass protostar maser J85. It shows that clearly in third, if continuum emission becomes clear upon calibration. So you see there is one spike here in the third if. So, and also as I mentioned before, our data processing capabilities allow us to show both maser lines. So if we would only use continuum emissions, these two maser lines would be overlapping and we wouldn't detect both. So it's kind of important to use continuum and line calibration. So clearly see that cross correlation spectrum of 66.7 gigahertz methanol maser in monitoring will detect flaring of individual spectral components. So now I showed some initial results that we have currently. So you see two things. So in the left you see the spectrum, so how the spectrum is changing over time. This is maser spectra for 66.7 gigahertz high mass protostar G85. So in three-dimensional plot you see observation dates and velocity of each spectrum and see how the spectrum changes over time. in the left plot, you see. So you see there is two components of measure. So blue and orange lines are trace of the variation of radial flux of measure. So we have two components, minus 29 kilometers and 31 kilometers per second, and green line is continuum emission of same sources. So this is the idea that we have. It is to monitor at the same time measure lines and continuum emission. And also what I have not shown is showing the monitoring of calibrators. So that would be addition result would be monitoring of AGN quasars and sources like that. So and in the short, so this result is also proposed in next Latvian Council of Science project proposals. So our task is to you create a transient program, so to detect transients, and thank you for your attention.
Thank you, Jānis. So do we have questions from audience? Oh, while the questions are being thought of, maybe a quick one from my side. So in the previous slides where you showed the graphs of initial monitoring results, there were, this one. So on the graph on the right side, there are relatively few flux points observed basically within a month or so. Would it somehow make your work easier or more precise in case there were more points observed over longer periods of time?
Yes. So initially, what we did, we start to work on plan how to do these kind of observations. So initially, we didn't thought that we need to, for example, do correlations in line and continuum. So first part of this kind of project was a technical development. So, and also, as you know, this project is currently cut off because of problems of edges and measure. So yes, you're right. So if you have more observations, so I think in future we will need more observations in many observations, maybe observations per week or many observations per week. So.
Okay, and as you mentioned, the technical development for this type of project, could you maybe in few words explain or sketch in what hardware is used and how do you deal with the SFXC correlator? Is it something that you're developing here at VIRAC as well, or it's strictly in collaboration with people in Netherlands?
No, so the SFXC correlator is installed on VIRAC high performance cluster, and all the other software, Delta software is also installed on the cluster. So we run all the data processing on our cluster, so there's no problem in that way.
So would you say that our local HPC clusters are capable enough to fully support this type of correlation for a local baseline?
Yes.
Okay, thank you.